The Earth has a mass of 6 times 10 to the 24 kilograms. Show that the gravitational field strength of the Earth is equal and opposite to the gravitational field strength of the Sun at a distance of 260,000 kilometers from the centre of the Earth. Now, I've got one other piece of information that we actually need there, which is on A2 above, which is the Earth's orbit is a set distance of 1.5 times 10 to the 11 meters from the Sun. Okay, so I'm going to do this fully, and I'm going to do it in terms of proving that figure that they've given in terms of the separation, because this is a common style of multiple choice question that comes up and people struggle with. It comes up not in terms of gravitation, but in terms of electrical fields, in terms of balancing two things. So what we've got there is we've got the Sun and we've got the Earth, and we know they are at a separation, because they're in orbit, of 1.5 times 10 to the 11 meters. We know the mass of the Sun is actually equal to 2.0 times 10 to the 30 kilograms. Make sure I read that as a 30. And we've got the mass of the Earth is 6.0 times 10 to the 24 kilograms. And what we're really looking for is this magical point in the middle, somewhere. This point I'm just put as a dot, when the gravitational pull towards the Sun is equal to the gravitational pull towards the Earth. Now I'm going to say that that happens at a distance RE from here to here. So that's the distance from the Earth. And then the distance here is going to be the distance from the Sun. At that point, we want to have the gravitational field strength from the Sun to there to be the same, but in that direction, and the gravitational field pull from the Earth to be the same magnitude, but in that direction. We can obviously work out G at any point by using G is equal to G m upon r squared. So if I actually set this up, what we've got then is G, so if I work it out for the Sun, I've got G mass of the Sun upon distance from the Sun squared, and that must be equal to G mass of the Earth upon the distance from the Earth squared. First thing you'll notice is the gravitational constant cancels. The second thing I'm actually going to do is rearrange it ever so slightly. So what I'm going to rearrange is to give me is I'm going to have the RE squared upon RS squared is going to be equal to ME upon MS. So I've just flipped these terms around, bringing the RE up there and doing the MS down there. And that means I can actually also square root them. So that's going to tell me that RE upon RS is going to be equal to the square root of ME upon MS. And we've got the numbers for that. So I know the mass of the Earth is 6.0 times 10 to the 24. And I know the mass of the Sun is 2.0 times 10 to the 30. Square root those, and that must tell me the ratio of these distances. So if I grab the calculator, put in 6e to the 24 divided by 2e to the 30, square root of my answer gives me 1.732 times 10 to the minus 3. And there's no units because it's just a ratio. Now I didn't actually have to put these numbers in at this point. I just did to make it slightly easier going forward. Strictly, or the best way to do it, would just be to keep with the algebra. Because by doing this I've sort of lost some precision. Alright, now, what does this really mean? Well, that means I can write the distance from the Earth must be equal to 1.732 times 10 to the minus 3 times by the distance to the Sun. But we've got something slightly better that we can write, because if I actually look at the top up here, I can see that RS, so the distance from here to here, RS is actually equal to 1.5 times 10 to the 11, so it's the whole thing, minus the distance RE. So I can actually substitute that in. So I've got 1.732 times 10 to the minus 3 times by 1.5 times 10 to the 11 minus RE. And I take that, and I can actually, again, multiply these terms out. I wouldn't normally, but it's just going to help kind of in terms of our understanding. So if I multiply these terms out, what I'm going to get is 1.732 e to the minus 3 times 1.5 e to the 11 gives me 259.8 times 10 to the 6. So that times that, and I'm also going to have minus 1.732 times 10 to the minus 3 RE from that times that. That means I can rearrange these and I can say that RE, I've got 1 this side plus 1.732 times 10 to the minus 3 for that bit has got to be equal to 259.8 times 10 to the 6. Therefore, I'm going to have RE is going to be equal to 259.8 times 10 to the 6 divided by 1 plus 1.732 times 10 to the minus 3, which would give me, divide that by 1 plus 1.732 e to the minus 3, gives me, still pretty much going to be the same things, it's pretty much divided by 1, gives me 259.35 times 10 to the 6 meters. So we've got that distance from there to there is 259 times 10 to the 6 meters. Now if you write, well, you can actually say that distance is actually, just round it up, say, well, we've got that's 260 times 10 to the 6 meters. 260 times 10 to the 6 would be 260 kilometers, 260 times 10 to the 3 kilometers, or 260,000 kilometers, which is what they stated in the question. So I've actually answered the question, proving that the distance that this happens is actually 260,000 kilometers. Now, there's another way I could approach it. What I could actually do is plug their numbers in, which is simpler, but is probably a little bit too easy for A2. So if I look at this, if I look and consider the Earth, we're still going to be using G is equal to Gm upon R squared. And what I've got then is going to be 6.67 times 10 to the minus 11. I'm just substituting the numbers. The mass of the Earth, we had 6.0 times 10 to the 24. And that distance is going to be 260 times 10 to the 6 in terms of meters, actually squared. So G, the force here in this direction, because it's due to the mass of the Earth, is going to be this. Plug the numbers in. 6.67 e to the minus 11 times by 6.0 times 10 to the 24. And I'm going to divide that by 260 times 10 to the 6, and I'm squaring that. Gives me 5.92 times 10 to the minus 3 newtons per kilogram in this direction, so from here to here. If I consider then the force from the sun, I'm expecting it to be the same, but in the opposite direction towards the sun, so I've got G is equal to Gm upon R squared. 6.67 times 10 to the minus 11 times, I need the mass of the sun, which is 2.0 times 10 to the 30. Divide that by, now I want the distance from there to there, sorry, from there to there, so I'm going to have to do 1.5 times the orbital distance less RE. So I've got 1.5 times 10 to the 11 minus RE, which is 260 times 10 to the 6, and then I've got to square that. So, plugging those numbers into the calculator, I have got I'm going to do the bottom first. 1.5 times 10 to the 11 minus 260 times 10 to the 6, and I can square that. Then what I've got is 6.67 times 10 to the minus 11 times 2e to the 30 divided by my previous answer gives me 5.949 times 10 to the minus 3 newtons per kilogram. So you can see that these two numbers, certainly to two significant figures, are the same. So you've got the magnitude is identical, the direction is opposite. Thank you very much.